Hello, good afternoon. First of all, I would like to thank the organizing committee for having me. Today I will talk to you about people patterns of Hadamard Matrices order 20. Um, First of all, what we wanted to do in this work was to identify the possible pivot patterns that can emerge when we apply Gaussian elimination to complete pivoting to an Hadamard matrix of order 20. We used a computational approach and we wanted to discover as many of these pivot patterns as we could by randomly generating Hadamard matrices from ones that we already knew, applying GECP to them, and recording their pivot patterns. Some background, I assume you're all generally familiar with Gaussian elimination, so I won't go into much detail. It is, of course, a very widely used algorithm with multiple applications. There is a major unresolved issue regarding the algorithm, and specifically concerning its stability. If we allow row swaps in partial pivoting or row and column swaps in complete pivoting, in order to ensure that the pivot at each step has the largest possible absolute value in the remaining submatrix, either within its own column for partial pivoting or within the entire remaining submatrix for complete pivoting, we get the algorithms GEPP and GECP respectively. In this work, we're interested in GECP, and the reason for this interest is that the backward error analysis of GECP, the growth factor of the matrix to which it is applied arises as a quantity of interest. And of course, finding a relatively low upper bound for this quantity would imply that GECP is not just stable in practice, but also theoretically stable. So let's begin with some basic concepts. If we denote AK, the matrix that results from A after having performed k-1 steps of GECP, then for k up to n-1, the kth pivot is the maximum of all the absolute values of the bottom right submatrix of AK, starting at the kth row and column of AK. And the final pivot is the absolute value of the bottom right element of the final matrix. Then the growth factor of the matrix A can be defined as the maximum of its pivots divided by the first pivot, which is the absolute value, the maximum absolute value of any element of A. And since in the definition of the growth factor, the pivots appear, this means that the pivots and the pivot pattern itself, which is the sequence of pivots, basically, also arise as quantities of interest. Also, I would like to note that whenever we use the term pivot in this work, we mean its absolute value. I'm supposed to be talking about Hadamard matrices. So what is an Hadamard matrix? An Hadamard matrix of order n is a square matrix of order n, with all its entries equal to plus or minus 1, such that when we multiply it with its transpose, the result is n times the identity matrix of order n. An Hadamard matrix can only have orders 1, 2, or a multiple of 4, although we don't actually know if an Hadamard matrix exists for each of these orders. It has been conjectured that the growth factor of any matrix is at most, of any square matrix, is at most equal to its order, with equality if and only if the matrix is an Hadamard matrix. The inequality has been proven false in exact arithmetic by modifying the counterexample that did not account for rounding errors. But whether or not the second part is true, whether or not all Hadamard matrices have growth factors equal to their orders, is still unknown. It remains an open problem. We know that it does hold for small orders, specifically up to order 16. For 1, it is trivial. For 2, 4, and 8, it was proven by Day and Peterson in 1988. For 12, it was proven by Edelman and Mascarenhas in 1995. And most recently, it was proven for order 16 in 2009 by Kavaridis and Professor Vitruvic. And in this work, what we're doing is we wanted to propose some algorithms that can be used to randomly generate Hadamard matrices of any order really, but specifically order 20, from ones that we already know, and compute their pivot patterns to find new pivot patterns. This can be useful as a guide for more theoretical results, as was the case for order 16, where all the 34 possible pivot patterns were discovered computationally before a theoretical proof was given. Now, in the algorithms, we're using some auxiliary functions and one method of vectors. I won't go into much detail. We can generally get the sum of all the elements of the given collection, vector, matrix, or set. We can choose randomly one element or any number of elements that we want, randomly and uniformly, from a given finite set or vector. We can append an element to a vector. We can count how many times an element appears in a vector. We can construct a vector of any length, a zero vector of any length, and a zero matrix of any dimensions. We can get the length of the vector and the size of the matrix in both dimensions together or each one separately. We can construct a vector by starting at a given number A, moving at increments of B, and going on until right before we surpass a given number C. And if we omit the step, it is simply 1. We can get the ith element of a given vector V. And if for I we give a vector instead of a number, we get the corresponding subvector. And similarly for matrices, we can get an element of a matrix or a subvector of any of its rows or columns, or any submatrix of the matrix. Now, onto the more theoretical aspect of this work. Two Hadamard matrices of the same order are called equivalent if we can get one from the other after a finite number of row swaps, column swaps, row negations, and column negations. This gives an equivalence relation, and the following table shows how many classes exist for some small orders. Unfortunately, equivalent Hadamard matrices may have different pivot patterns, which means that simply finding the pivot pattern of one representative from each class is not sufficient. However, we can use this to our advantage in order to find more pivot patterns by generating other Hadamard matrices from ones that we already know and computing their pivot patterns. This algorithm generates a set of information that can be used to describe such a transformation. It chooses a number of operations to perform, from 1 to 200 in this case. Then it chooses for each operation of which type it will be, counts how many operations of each type will perform, and then for each operation, for example, for row swaps, we choose which rows to swap, randomly again. Similarly for column swaps, and then it chooses which rows and columns to negate, and returns the information. Now, if we have such a transformation description and a given matrix, then we want to be able to transform the matrix, which we do using this algorithm. It goes through all the operations and simply performs the necessary changes depending on the type of the operation. This is how we do row swaps, and then column swaps and row and column negations respectively. And finally, we return the matrix. To find the pivots of the matrix, we can apply Gaussian elimination with complete pivoting to the matrix and keep the absolute values of the elements that appear in the diagonal. Again, I won't go into any detail about how we're doing this. And finally, we return the pivots. Now, our next algorithm can be used to find pivot patterns. We construct a matrix that contains the ones we may have already found as its rows. And then it also constructs a vector that counts how many times each pivot pattern has appeared. And then it generates such a transformation as described before. It transforms each of the chosen representatives that we have in the list R according to that transformation, and finds the pivots of the transformed matrix. It checks if they're new. If they're not, it simply increases the count of how many times they have appeared. If they are new, it adds them as a row to the matrix N, appends the count 1 to the end of the vector counts, and stores all the relevant information. Counts is stored regardless of whether or not the pivot patterns are new. The pivot pattern is new. And finally, we can go through, we can construct M as before and go through its columns and find all the unique values that can appear in each column. And those are the possible values that the corresponding pivot can take. We implemented these algorithms in the Julia programming language using rationals to avoid random errors. And we took the representatives for each class from this website. we use our algorithms to confirm the results for order 16, and in all test runs, all of the 34 pivot patterns were generally found within a matter of minutes at most, requiring at most a few 100,000 matrices, which showcases the efficiency of the algorithms and indicates that they are indeed correct, as well as the implementation. The first attempt at recording the pivot patterns of Hadamard matrices over the 20 appears to have been in the reference you can see below, yielding 1,015 pivot patterns from 3 million matrices. This number was then raised to 1,128, and now we're raising it to 1,246 from so far 3.05 billion matrices. Here you can see all the pivots, all the values that we have found for each pivot. You can see the first one. The last one appears always with 20, which is the matrices, and then everything else appears to be 2, and 10, which is half the matrix, of the matrices. Here you can see the number of times each pivot pattern has appeared from most to least common. Here you can see all known values for each of the first 8 pivots, and for each of the last 8 pivots. And the ones that I didn't mention before, how we have found 36, 118, 89, and 17 values, respectively. Possibilities for future research directions include potentially approaching the problem in a theoretical manner, or improving our algorithms, and extending this approach to work for higher orders, which is generally very straightforward. That's about it, I guess. Thank you for your time.
Thank you, speaker. I have a question already. Understand how difficult it is to solve the problem from 16 to 20. It is well known that Hadamard matrices are very useful in many areas, like statistics, like numerical linear algebra, and recently in neural networks. And I understand that for the case 20, you have a lower bound for the different pivot patterns. Is it true?
Yes, I mentioned it.
My question is it possible to have an upper bound?
I don't think I've seen any research regarding that. There are some theoretical results that can be found by using the possible determinants of minors of certain sizes of Hadamard matrices. And I guess if we take all the possible combinations of the determinants of +1 matrices, we can probably get an upper bound, but it's probably not very good.
Okay, thank you. Is there any question from the audience? Check.
No.
From online?
Yes, nothing.
No.
No.
We thank again the speaker.